So welcome back. We are still with the lines of field, and I gave you the explanations with a couple of examples where we can calculate the electric field in certain situations which have got an element of symmetry along with an element of geometry. Okay. Now, today what we are going to do is, we are going to tell you how the electric field can be calculated for a number of discrete charges around a certain point P. And then we'll discuss the physical significance, if any, of the electric field concept, which I told you that's merely a concept. Electric field cannot be measured without the measurement of the force on a known charge, which we call the test charge. Okay. But nevertheless, there is a physical significance assigned to the electric field in another aspect, which we are going to discuss today. I'll just introduce it to you. Well, if there is a set of n discrete charges, Q1, Q2, Qn, and we wish to calculate the field at a point capital P. Okay. And if we calculate the field due to individual charges which are not disturbed at all, then we will have fields E1P, E1, E2P, ENP, etc. Okay. Well, this I can just say that maybe there are so many fields like this, etc., that we are going to calculate. Then what happens? What is the net field? These are all vectors, and the vectors will add according to law of vector addition by the principle of what we call superposition. I did talk to you about superposition before and now also. In the case of waves, I talked to you, and this will be the principle of superposition will go on with us, and we will keep on doing that. Okay. So I can write this like this. Now, the first one, E1P vector, can be written as 1 upon 4 pi epsilon naught, which occurs time and again. So I have taken it out of the bracket. Q1 upon R1P square, R1P cap. Q2 upon R2P square, R2P cap, etc., etc. So I can write it in a very compact form as 1 upon 4 pi epsilon naught summation I is equal to 1 to n Qi upon RIP square into RIP cap. Okay. So this is not very difficult. It's just one time you write that, and you'll remember it if you go by the cyclic order. Okay. Which is built in inside us. Now about the physical significance of the electric field. Okay. In the first instance, I would like to tell you that for electrostatics, for purposes of electrostatics, where the charges are not moving at all, the concept of electric field is just a convenient but not really a necessary thing. We can do with the calculation of forces on a test charge and then work them out, and our purpose is solved. Well, but the concept, it gains significance. It is an
elegant way of characterizing the electrical environment of a system of charges. When I say electrical environment, in that some of the charges may be fixed and some of the charges may be moving. And when that movement occurs, the movement of a positive charge like this or a movement of a negative charge like this, that gives us the flow of electric current according to the concepts that you have picked up in your high school classes. What is electric current? It is a flow of charges from positive charges, from levels of higher potential to levels of lower potential. Well, there is a problem. If the charges are fixed, we are talking about electrostatics. But when the charges are moving, when the currents are there, then there arises something which is known as a magnetic field. So the electric field that I have given to you is E, and the magnetic field that will occur there is B. Both are vector quantities and they are intertwined with each other, as I will tell you. So the true significance emerges. Significance of what? The physical significance. The true physical significance emerges, comes out when we go beyond electrostatics to electromagnetics. Now, for example, let us consider two charges Q1 and Q2 located at two locations, 1 and 2 respectively. Okay, 1 and 2. And now, very interesting thing is that if a charge is accelerated, then an accelerating charge gives rise to what is known as an electromagnetic wave. What is a wave? Wave is a means of propagation of energy from one point in space to another point in space. It carries with it information, also carries with it energy. Okay. So what is going to happen? What is going to happen is, because of the motion of this charge, accelerated charge, there will come up electromagnetic waves. And these electromagnetic waves, they propagate all over the space. And in doing so with a velocity c, okay, with a speed c, c is the speed of electromagnetic waves or the speed of light in vacuum. We are just taking the things, everything to be happening in vacuum. Now, the waves, what do they carry? They carry the information, they carry the data, they carry the flag, okay, the stuff of the production of electromagnetic waves. So with that flag, with that information, the waves reach Q2, okay, and register their presence with Q2. But because the waves are moving, they are moving in the finite speed c, it takes some time. The time taken, okay, the time taken, that is, there will be a time delay which will be, if the distance between these two is r, so r divided by c will be the time delay when the information will come to Q2. That look here, Q1 is moving and Q1 is having an accelerated motion. Okay. So it causes a force on Q2. Okay. It causes a force on Q2. So this is the cause and this is the effect. The force over here is the effect. In fact, we will see in the due course of time that when a charge moves, then the associated electric field is also changing with time, because the location of the charge is moving with time. Therefore, the field becomes time dependent. The electric field becomes time dependent, and the field is in space. So now there are two things. One is called the space and the other is called the time. Okay, space, time. Space means coordinates x, y, z, and time means the coordinate t. Okay, so I can say that my electric field is changing with respect to time. So there is a dE dt, there is a dE dt. This dE dt, what it causes is causes a dB dx, a dB dy, a dB dz. That means there is a changing magnetic field with space, and whenever the associated magnetic field changes in space, there is a corresponding change in the time change in the value of electric field. So there are two things, two aspects. There is dE dt, there is dB dt, there is dE dr in space, and there is dB dr. Or if we take the wave only in one dimension, then I have a dB dx and a corresponding dE dx. Now, these things, the time rate of change of the electric field and the time rate of change of magnetic field, the space rate of change of the electric field and the space rate of change of magnetic field, they intertwine to give what are known as the elegant electromagnetic waves. Okay, so there's there to explain them, to obtain the relations, and to correlate. I told you we will correlate this epsilon naught, mu naught, and c, they together, and these are the properties of the space. Not only in vacuum, which is called nothing, something called nothing, or as empty space, but because the value of c will be less than the speed or velocity of light will be less in material media as compared to in vacuum. These are certain things we have to talk again and again so that you are able to understand. So this is about the physical significance of the electric field. Now I am going to discuss to you which I have done before, but I will take it in more strides than before, and that is the electric field lines of field and the concept of the flux of fields. So electric lines of field, as I told you, I am going to introduce that and historical. These lines of field, which are also called electrostatic lines of field, that we take from Michael Faraday. Michael Faraday, the genius. Michael Faraday, the self-made scientist. Michael Faraday introduced lines of force. Okay, for a long time, lines of force, lines of force, lines of force, until the lines of field concept that come. The field concept came, and then since then
we abandoned that lines of force concept. Okay, and we talked about lines of field, etc., etc. Okay. When we draw the lines of field from a single charge initially, then we see that the length of the lines of field keeps on reducing as we go away from the point at which the charge has been placed. The lines of field, normally they are straight lines, but they can be curvy also. And if they are curvy, and like this there is a curve, and we just consider a point on that curve and draw a tangent, that tangent gives the direction of the lines of field. Okay, then we can draw for very simple charge configurations lines of field for a positive charge, for a negative charge, for a pair of charges both positive, and for a pair of charges which constitute what is known as a dipole. One charge positive, the other charge negative. I am not drawing these lines of field for these simple configurations, but they will appear here on the left hand side of board, and you can see them as to how these lines of field, they go away and then go towards starting from infinity, etc., etc. Okay, so you can look at those. Here in between this Q and Q, there will be a region over here where there will not be any electric field. So they will appear to have, for the equal charges that we have, there will be a neutral point that will be evident in the third drawing on your left. But in this case, so these are the field line mappings which are appearing over there because they are drawn professionally, so I am not going to draw it here. Okay. Then let us see if there is a charge here and the lines of field are going in all directions in a this thing, in a sphere, through the spherical lines or into the spherical surface, etc. Then, as I told you before also, and I told you about 1 upon r square dependence, this is a cone, okay, which we can make with the help of a, and not very long before, some chanajor garam used to be sold in such kind of cones. Still such cones made out of paper, simply they are available, and people they sell groundnuts and other things in that. Look here, what I have for the cone, I have a spherical, a rather a circular thing drawn on the spherical surface, which if you can see that as we go to this, then if suppose like here I have 5 lines coming out of it, then these lines, they come out of each of these surface areas, and the radius keeps on reducing. But if I have a small area delta S perpendicular to the flow of lines of field, then we find that maybe here the number of lines which are passing through it is equal to 3, then it may become 2, then it may become a single line, etc. How many lines we can draw from a point
I told you that if you draw n lines from a charge small q, then you will have to draw nn lines from a charge which is nq. Okay, it all depends upon yours. So it will, it is said, but anyway, there is a relation that exists, and this I told you in that case. So let us see what are the salient features, what are the properties of field lines. So this is a set of properties that I am enumerating over here. Number one, field lines start from positive charges and end at negative charges. So if there is a distribution of charges, then the field lines will start from positive charges and end at negative charges. Okay. For single charge, whether positive or negative, they may start or end at infinity, like in the case of these two charges that appear in the figure number 1 and figure number 2 on your left. Okay. Well, I said that the lines of field are often broken lines of, when you go away from the charge, it is of broken line with reducing length. Okay. But in a charge-free region, why? Because they start from a positive charge and end at a negative charge or negative charges. In a charge-free region, if there are no charges there, positive or negative, we get continuous curves without any breaks. Okay, so continuous curves may be obtained without any breaks, no breaks. Another feature about the lines of field is, whatever kind of lines of field, that two lines never cross each other. Because if suppose we have two lines and they are crossing each other, then if I take this line, then the net electric field is like this, and if this line, the net electric field is like this. It's not possible, because lines of field give us the net electric field, and there should be a unique value. Okay, unique value. So two lines can never cross each other, because you cannot have two values for the same thing. Therefore, if they do so, and if somebody says that this is like this, there is a violation of what is known as uniqueness. Okay? Okay. Now, there is another interesting feature for electrostatic lines of field, that we do not have any closed loops. Closed loops. Okay? Which is possible in the case of magnetic lines of field. Okay? So, why? Because in a magnetic lines of field, we can have, for a small bar magnet or any magnet for that matter, there is a north pole and there is a south pole. Okay? The field lines go away from the north pole and they enter into the south pole, and thus a loop can be created. Magnetic monopoles is not a possibility. Okay? Magnetic poles, they appear in pairs, but electric charges can exist, they are monopoles and can exist with monopoles, and because there are monopoles, so therefore closed loops are not possible. So these are some of the four features associated with the electric lines of field. Okay? Well, here this composition, this configuration that I have shown to you, conical configuration, I can show that here on this there is a surface like this, and the lines of field are going out of it. Okay. Then if there is a ds vector, okay, then there will be a flux out that can be given as E dot ds. And what is E dot ds? ds or delta s, let's take it like this, E dot delta s or E dot ds. Now this is called the flux out or flux in. That is dot product. So what is the output? The output of a dot product is always a scalar. So whatever is going out of it, or whatever can enter through that, or for that matter, if I have a surface like this and the water is flowing like this, then this will be obstructed. Or if I am only talking about a loop like this, okay, water will go out of it, but if I change the direction, then less and less water will go out of it, less of a thing will go out of it. And when the surface becomes, this is the ds and this is the electric field or magnetic field or gravitational field, when we have it like this, then as you know that this surface ds or delta s or whatever, it is perpendicular to the surface under consideration, and therefore the flux out will be equal to 0. So E dot ds is what I will talk to you about, and I expect you to read it from your text, and when we meet again, then I will explain it out, because this flux in, flux out, this actually leads us to what is known as Gauss law. Gauss law is in the name of Gauss, a German scientist or mathematician or whatever you want to call, and the story goes that Gauss was very intelligent, and there was a teacher in those days. Teachers used to come to the houses of the elite, the haves, and teach the students at their place. Gauss's teacher used to treat so many students, used to walk down from one place to another place, another place, another place. So one day when he came to Gauss' place, Gauss came out with his pen and or pencil and slate or whatever, and he came to his attendance. But the teacher was very, very tired. So he thought, let me give him a task. And he said, okay, Gauss, please sum up numbers 1 to 100. And then he sat in his chair and wanted to take a quick nap. By the time he reached there, Gauss told the answer. And this man, who had spent some time while he was walking down to this house as to how to do that, he was just amazed. And he started shouting, how can you? You are cheating, this, that. His father came and he asked Gauss' father, and when he came to know about it and the complaint of the teacher, he asked Gauss, hey man, how could you do it? He said, it's very simple. I take 1 and 99, 2 and 98, 3 and 97, etc. So I make so many pairs. Each pair is 100. Okay. So I get so many pairs plus 100. So many pairs, I just multiply that and I find the value is, you know that, okay, how much it is. And so that Gauss, he came out with a law, Gauss law, and that is the beautiful thing. I will tell you about it, Gauss law, and if you get time, just look at it, how Gauss law is an equivalent in calculations, in estimations, as to the Coulomb's law. We can derive the Gauss law from Coulomb's law, and we can derive the Coulomb's law from Gauss law. So we will do these things in the coming few outings. Thank you very much for being with me. I stop.